Okay, so it's our great pleasure to have our first internal speaker for this 24, 25 fiscal year. So basically we have Jong Lee from our physics department and also iQuiz to present his recent work. Jong got his PhD from Harvard University in 2020s, and then he moved to Cavity Institute of Theoretical Physics, and then he joined our department this year. So he's going to talk about his recent work on open quantum system and spontaneous symmetry breaking today. And let's welcome Jong.
Thank you, Peng Jie, for introduction. So as he said, today I'll introduce new types of spontaneous symmetry breaking that can happen in open quantum system. So open quantum system is actually quite interesting from the following point. If you think about like closed quantum system and unitary perturbation, although there can be a lot of interesting happening there, it is essentially a change of basis. So if you think about information, it cannot be neither created nor removed under unitary perturbation. But when we have an open quantum system, there can be some exotic type of evolution, such as a measurement, where wave function collapses in a way consistent to the observation. And it can decohere, where wave function evolves in a way unknown to us, because decoherence corresponds to effectively an environment measuring your system, but not telling you what the outcome is. So your wave function now evolve into an ensemble of pure states, and it cannot be captured by a pure state wave function. So now the information is something that can be manipulated or discussed at all in this open quantum system. One can think about many-body physics of information, in that instead of considering conventional kind of physical observables like structural pattern, conductivity, magnetization, you're talking about whether the system is thermalized or not, whether there's any entanglement that can be used as a resource, is there any memory capacity as a quantum memory, things like that. And when we are discussing this kind of information physics in this like many-body quantum system, one can ask whether there is any unifying principle. Before going into detail, let me introduce a little bit about the mixed-state formalism for someone who might be unfamiliar. So when you have a quantum system, size 0, even if you start from the pure state, if the environment is coupled to your system and randomly apply some perturbation, then your system can evolve into an ensemble of pure states, each of which comes with some probability pi, such that if you describe this evolution by some quantum channel epsilon, your initial pure state density matrix evolves into basically a set of different ensemble of pure state, which is captured by this density operator. And one nice trick in this mixed state formalism is called a Choi isomorphism, where you're basically vectorizing 2 to the n by 2 to the n density matrix into the 4 to the n by 1 vector living in the double Hilbert space. So this is nothing but just a vectorization, so it's a faithful mapping. And because now it's living in the double Hilbert space, you can imagine this pure state living in the kind of bilayer system. And decoherence is nothing but just some sort of kind of coupling between these two layers. So in this way, problem reduces to the study of pure state, and it's just like notational convenience, because condensed matter physicists are so familiar with the pure state formalisms. And now that we have a double Hilbert space, one may imagine the symmetry might be doubled as well. So if you originally have some symmetry G, and if you consider the density matrix for this pure state, your density matrix will be invariant under left action or right action of the symmetry operator. And we call that as a strong symmetry. But if your density matrix is only invariant under the conjugation by the symmetry, like in the second case, we say that there's a weak symmetry. From the doubled Hilbert space formalism, you can basically say that there's a strong symmetry means that the double state is invariant under the action of the UG on the first layer or the second layer. But if you only have a weak symmetry, that means that it's only symmetric under this action in both layers. And in this sense, one can say that this is strong symmetry is like a doubled symmetry, and weak symmetry as a diagonal symmetry, because it is basically invariant under the diagonal subgroup of this double symmetry. So now let's switch the gear a little bit, because spontaneous symmetry breaking has been such a great kind of starting point to understand many-body phases of matter. One may think that the spontaneous symmetry breaking picture may give some intuitions about this many-body physics of information as well. So just to give you some example, the understanding family of different lattice structures, they are really the results of continuous translation symmetry breaking into the space group. Famous superconductivity is the result of U1 spontaneous symmetry breaking, and magnet is the result of spin rotation symmetry breaking. So yeah, I'd like to use this idea to understand the open quantum dynamics. So if we think about some classical partition function, the density matrix for the kind of classical ensemble of states, let's, for example, think about classical Ising model, which is just like a nearest neighbor ZZ interaction. This density matrix is basically a diagonal in this Z spin basis. And if you think about Ising symmetry for this Hamiltonian, which is a like product of X, basically a spin flipping the Z spin, you can see that there's no strong symmetry for this density matrix. Rho is not invariant under left action or right action of this UG. But you can see that this is basically invariant under the simultaneous action of the left and right UG. So this classical ensemble of states has the weak Ising symmetry. And if you think about this, it's pretty obvious, because when you think about classical ensemble of states, quantum coherence with respect to the symmetry charge is lost. So you don't expect anything kind of interesting about the off-diagonal elements of this density matrix. So in this sense, when there's no strong symmetry but only a weak symmetry, one can say that system is somewhat classical with respect to the symmetry. So you can think about spontaneous symmetry breaking starting from this two different setup. On one side, you have a strong symmetry, which is like when you have a pure symmetric state. And the other side, you have a weak symmetry, which is the ensemble of quantum states given by, say, a Boltzmann distribution. So if you think about spontaneous symmetry breaking from this left side, we say this is a kind of quantum kind of spontaneous symmetry breaking. So if you have a 2D quantum Ising model, this phase transition is actually captured by a 3-dimensional classical Ising universality class by this quantum classical mapping using Euclidean path integral. But if you have a same dimensional 2D Ising model, but classical, this phase transition from the weak symmetry to the spontaneous symmetry breaking will be 2D Ising universality class, meaning that these two sides are indeed something different. There's something intrinsically different about these two different symmetries. So because these two phase transitions are different, one may imagine that going from strong symmetry to weak symmetry by decohering the system, making it more and more mixed, there might be a phase transition, which can be only captured by the information-theoretic sense, because whether the distribution of the quantum state is, kind of quantum with respect to certain symmetry or classical with respect to certain symmetry is probably not something that can be directly measured by certain physical observable. So if you imagine your system undergoing some dynamics by being coupled to the environment, where this error operator or operator that environment is randomly applying to system is a strongly symmetric dynamics, I can try to think about whether there's such kind of strong to weak spontaneous symmetry breaking, because I'm going to maintain the strong G symmetry throughout the entire dynamics. But I'm going to basically ask still can there be a spontaneous symmetry breaking of G cross G down to its diagonal subgroup? And indeed, I found a set of models where this kind of transition is observed. And next thing you can ask is, okay, if there's such a transition, what is the like a quantity that defines this transition? So to understand this better, we may have to review how the spontaneous symmetry breaking is detected from the pure state physics. So when you have a Hamiltonian in a symmetry group, you can define some order parameter, and you apply an infinitesimally small symmetry breaking field such that after applying this small field, you measure how much order parameter has changed, and you first take a thermodynamic limit, and then now send the infinitesimal field to 0. And if this gives a non-vanishing expectation value, you say that there's a spontaneous symmetry breaking. So the reason why we have to apply this infinitesimal field is pretty obvious if you think about transverse fieldizing model, because even if you're in the like a ferromagnetic phase, your true ground state will always be this kind of cat state if your system size is finite. So in order to lift, so if you just naively measure the order parameter, it will be 0. So if you want to lift this degeneracy, you have to apply an infinitesimally small field such that the ground state is indeed ferromagnetically ordered, and only in this limit, symmetry breaking can be properly diagnosed. So from the same spirit, we can try to perturb this strongly symmetric density matrix by an infinitesimally weak channel, like that, which breaks the strong symmetry down to a weak symmetry, captured by this channel epsilon, E epsilon. And then I'm gonna measure quantum relative entropy between the original state and this slightly deformed state. And then I'm gonna differentiate this quantum relative entropy by epsilon. And this gives a so-called quantity, so-called the Fisher information, which detects how susceptible your system is with respect to this symmetry breaking perturbation. So from the quantum information or AMO community, people talk about Heisenberg limit or how precise you can measure certain quantity in physical system, and that's directly related to the Fisher information. And I have several models where this Fisher information indeed undergoes this kind of phase transition. And what I'm going to claim is this really captures when your mixed state of quantum state kind of transition into the effectively a classical ensemble with respect to the symmetry. Any questions so far? Yeah, so here there is no Hamiltonian in principle because I'm talking about just density matrix and its deformation. But of course, you may think this density matrix under Toy isomorphism might be some ground state of some parent Hamiltonian. We may construct that, and that parent Hamiltonian undergoes a phase transition. That kind of thing you can use as some intuitive picture, but that's not always true. Yeah. Oh, because if you think about quantum pure state has if you think of a density matrix for the pure state, it is because psi is invariant under UG, the psi ket bra will be invariant under left or right action. So you double the symmetry. And the presence of this double symmetry kind of implies that there's something non-trivial in the off-diagonal element of this density matrix. Because usually when people talk about quantum kind of observable, this off-diagonal element is really important because that captures the kind of coherence, like some phase information. So when you have a weak symmetry, you can basically say that this density matrix ignores or suppresses all the phase information about the quantum states. But only when you have a strong symmetry, you can say that you're having a density matrix where those phase informations are properly taken into account. So specifically, for example, thinking about the Ising model. Here, I said that the symmetry I'm considering is this UG, right? Product of X. So if I consider a strongly symmetric decoherence, the corresponding error operator is like has a even parity under this UG, like a ZZ or ZZZZ, things like that. But when I'm introducing the symmetry kind of breaking channel, that will have a like odd number of Z for the error operator. So it has such a weak kind of strength. Yeah. Yeah, there are many ways to do it. It's same as like when you consider spontaneous symmetry breaking of pure state, there's a many way to apply kind of symmetry breaking field, right? Yeah, exactly. That's exactly the picture. Because in this because like if you think about kind of classical partition function, the two layers are density matrix diagonal, meaning that in this double space, two layers are just locked to each other, right? So locking between two layers is really a classic quality. That's not exactly what I'm looking at, but like if you have a pure state, then the two layers can be somewhat independent, right? Yeah. So I'm basically measuring the locking of two layers. That's what I'm measuring. Uh, right. Uh, Lindblad generator for right. Oh, right. So it's okay. Maybe that was so I'm already considering that your rho is evolved under Lindbladian under this dynamics, and then that is a strongly symmetric dynamics, and at certain point I'm trying to examine whether my density matrix, yeah. So indeed there are like a two Lindblad. This is just a probing field. This E epsilon is just a probing channel, and there's another channel that evolves the density matrix, which is dynamics that I pictorially showed earlier. Great. So based on this kind of principles, I'm gonna give you three case studies. The first one is Ising data symmetry, which is related to the Toric code error threshold very interestingly. The second case is fermion parity symmetry, which is related to the SYK model and whether traversable wormhole, if one side of the black hole is decohered, can you still maintain the traversability? The third case is the charge U1 symmetry, which is related to the charge transport dynamics. So Ising to symmetry. Ising is always our simplest example. So I'm going to give you how strong to weak spontaneous symmetry breaking happens in this model. So consider a channel, basically whose error operator is like a ZZ for every bond. And this is equivalent to basically measuring the ZZ for each bond with probably 2p. So as you're just measuring these bonds, would you undergo a phase transition? Naively, when you measure all the bonds in this like ZZ basis, then there will be some percolation. So you're gonna lose kind of charge coherence with respect to single Z, because if like ZZ is all specified, as soon as you know what the Z is for a certain site, you're gonna know what the Z is for the other site as well, which means that you're specifying what the Z is. So you're gonna lose your quantumness at certain point. And this intuition is correct. So let's say your initial state is a product state, a plus, where you basically, even if you measure what Z is at a certain point, you don't know what the Z is at the other point. And in the double Hilbert space, this rho 0 is the ground state of this Hamiltonian, which is H0 tensor I plus I tensor H0. And H0 is just like sum of squares. So its ground state is basically x equals 1, x equals plus. And under this mapping, the channel superoperator maps into a operator, which basically looks like this. And then, as Yuki asked, I wrote my initial Hamiltonian as a sum of square form. Then the new kind of parent Hamiltonian, which takes the choice state for this decohered density matrix as a ground state, is given by this A tilde dagger A tilde, where A tilde is epsilon A epsilon inverse. Because epsilon is not unitary, this A tilde will be non-Hermitian operator. But because I'm taking A tilde dagger times A tilde, this combined object is Hermitian. So this is a valid Hermitian Hamiltonian, which takes this density matrix as a ground state. So in the double Hilbert space, your physics is basically captured by two paramagnet with some coupling between layers, and it can be written in this form. So what's basically happening is that when you have like a ZZ coupling, and when the coupling is strong enough, you're gonna develop a condensate or mean field, the ZZ mean field between two layers. And the ZZ mean field will be invariant under the diagonal action of this double symmetry, but it's not going to be invariant under respective Ising spin flip. So there's certain like a critical point, and I can basically demonstrate that, depending on how you take the order of limit, there's a divergence of this Fisher information. And this Fisher information has exactly the structure of the susceptibility or order parameter square in the Ising model when you project into a suitable subspace. And basically what it means is that beyond this critical point, the system becomes extremely susceptible to a symmetry breaking noise, or basically the measurement that specifies what the Z is at a certain point. So as soon as you specify what Z is at a certain point, you're going to specify what Z is on all the other points. So you kind of lose the quantumness. Oh, my bad. So this x-axis is the strength of the error operator I'm applying here. So as I mentioned, if the P is getting larger and larger, you're going to lose the quantumness. So my question is, at which point do I lose the quantumness with respect to the symmetry charge? Yeah. Or I'm measuring with some probability, and I'm not measuring all. Yeah. And what's very interesting about this setup is that this setup is a dual to the Toric code under decoherence in like a Z error. Like you create some star anion, and basically you can ask, like if there are too many errors, you cannot do error correction anymore. At what point do I lose this error correctability? And this question is exactly dual to the question I was asking. And in the dual setup, what's happening is you have a two Toric code coupled by this ZZ kind of perturbation. And at a certain point, there's two copies of Toric code undergoes a phase transition into the single Toric code to a confinement. So since I talked about Toric code and topology order, let me make a few more remarks. So people say that Toric code is basically a quantum error correction code, in that even if you have some kind of error applied, by measuring all the stabilizer, you can locate where the errors are, and then you can correct them. But if there are too many errors, your error correction may introduce a logical error, and you may not be able to correct anymore. So the question you can ask is how to capture a fundamental bound on this error correctability or decodability. In the previous study by Daniel Skitaev, Landau Preskill, they constructed a maximum likelihood decoder claiming that, this undergoes a phase transition at a certain point, but it doesn't precisely answer the fundamental threshold intrinsic to the density matrix, because this kind of threshold depends on which decoding scheme you choose. So Thankfully, there's a very nice quantity called the coherent information that captures this fundamental threshold. So let's say you have a logical qubit, psi, and you encode it into the system by coupling to lots of additional ancilla qubit, and then you undergo decoherence. So if you want to like compare how robust your logical information is through the scheme, it may depend on the choice of the logical qubit, and like you have to also come up with all the like decoding scheme and so on. But let's say we want to be free of any of those kind of subtleties. Then basically what you can do is to bend the line of this logical qubit in the circuit diagram. And now you basically ask, what's the entanglement between the final output and this like a banded like starting point of the line? If that entanglement is unchanged or robust, then what it means is that in principle, there's information about your initial encoding that can be decoded out. But if that entanglement is getting smaller, that means that basically you cannot, this identity operation is degraded. So the robustness of this identity operation can be basically captured by entanglement in this like a banded circuit diagram. In here? No, it's totally independent. Yeah, anything. Yeah, any channel. Yeah. Yeah, this is still the correct. Yeah, this is like fundamental quantity called that upper bound any amount of decodable information. I forgot to put the citation. It's by Nielsen and Shamar, 1980 something, 87. So yeah, so this quantity is called coherent information. But entanglement between R and Q might be a little subtle than what you think. So if you naively measure like entanglement entropy of the Q, it's going to capture the entanglement with R, reference R, and also base E. But if you measure the entanglement entropy of R and Q combined, it's going to only measure the entanglement between Q and E, because there's no like coupling between R and E. So there's no entanglement between R and E. So by taking the difference between the entanglement entropy of Q and entanglement entropy of QR, you're going to get precisely the entanglement between R and Q. And that is the coherent information. So if this quantity is robust, then you can claim that, I don't know how to decode, but there is a quantum information that can in principle be decoded out. But if it's degraded, then that basically determines how much you can get out of this. So for Toric code, I can basically show that there's initially if you encode two logical qubits, that is kind of robust up to a certain threshold of like a X error rate and the Z error rate, and basically decreases after. The right-hand side, I'm plotting the coherent information with no decoding, no encoding scheme. There's basically two raw physical qubits. Here you see that basically the coherent information degrades kind of continuously. So by encoding into the Toric code, you can maintain this robustness. Yeah, so this coherent information exhibits some sort of phase transition behavior. That's maybe a key takeaway message. So the summary of this first case is that there indeed exists a model that exhibits strong to weak spontaneous symmetry breaking under strongly symmetric decoherence model. And this kind of like on-site zero form strong to weak SSB is usually dual to a kind of decoherence in this transition in the topology order by generalized Kramers-Vanier duality. So when you're interested in studying the error threshold of, say, Zn topology order or some sort of more general topology order, you may study the dual model under strong to weak SSB, and that provides you error threshold. And this kind of transition can be captured by various different metrics, like a Fisher information, as I showed, which I think is the quantity that is probably the most analogous to the pure state kind of physics. There can be a coherent information. There can be all the other different quantities as well. The second example I'm going to talk about is a fermion parity symmetry. So for that, I'm going to consider somewhat like exotic model called the Sachev-Yaki type model. So it is a model, the Hamiltonian is modeled by a Hamiltonian with a four-body Majorana fermion interaction, which can be rewritten as a kind of spin-spin interaction with kind of random kind of coupling strengths. So it's an all-to-all kind of interaction model. And you can also think about low rank generalization where there's a coupling JIJKL has a specific, more sparse rank structure. And this gamma is basically the quantity that captures the sparsity of the rank of this interaction. And as a function of gamma, people have shown that, okay. So this model is quite interesting for several reasons. It's exactly solvable if your system size goes to infinity. And it's connected to various different topics like quantum gravity, quantum chaos, non-Fermi liquid. But the property I'm going to focus on here is it's an extensive zero temperature entropy. So usually when you think about any quantum system, ground state degeneracy is like finite. But this model, it has a kind of quasi-ground state degeneracy, which is kind of exponential in the system size, meaning there is an extensive zero temperature entropy. And this entropy coefficient S0 is basically a function of gamma. So as your system is more and more complicated, if gamma is larger and larger, S0 is larger. But as your interaction is getting more and more sparse, S0 is getting smaller as well. So because of this extensive kind of ground state, quasi-ground state degeneracy, one may imagine to encode some logical information in this quasi-ground state manifold and ask whether this information to be robust under decoherence or not. And considering that this is precisely the physics important for the traversable wormhole, it's also a pretty interesting question in the context of high energy theory. So let me consider the SYK model coupled to the bath. And the decoherence model, so it's the following. So if I look at this SYK model, the only symmetry, microscopic symmetry it has is the fermion parity, because your interaction is a 4 Majorana fermion. It's invariant under the parity symmetry. So you can imagine two different types of noise models. The first one is a parity breaking noise, where your SYK model and bath exchanges Majorana. The second noise model is a parity conserving noise channel, where it's always a kind of pair hopping or interaction. So as I did in the previous step, I can try to encode this extensive information into the kind of ground state of the SYK model and look at its coherent information. But since it's a little tricky, what I'm going to use here is so-called a thermophile double with like beta goes to infinity limit. By using this thermophile double, I can basically encode, form the maximally entangled state between your system and the reference for this quasi-ground state manifold. And as I said, the recoverable information is exactly captured by this coherent information. So for this, I don't know, for the other case, I know how to calculate the von Neumann information theoretic quantity, but for this case, this is pretty challenging. So I'm gonna do basically a Renyi approximation, which is equivalent to the double space formalism. So in the like double Hilbert space, basically your decoherent density matrix is captured by kind of this kind of path integral. So you have a like this, the blue box corresponding to the preparations of the thermophile double, and the red box corresponding to the application of the error channel. And if I try to calculate the entanglement entropy of QR, it corresponds to this path integral. So under the absence of error channel, it basically decomposes to two disconnected loop diagrams. And the entanglement entropy of like your system is kind of this complicated looking path integral because you trace out R first. But anyway, under the absence of this red box, it's just a single path. And this path integral nicely have a just a Euclidean path integral structure, and it can be calculated using Schwinger-Dyson, numerically calculated using Schwinger-Dyson equation in the large n limit. So, and the higher Renyi version can be also calculated similarly by considering this higher order copies. And let me just like flash out the result. So if you think about parity breaking error, you can see the coherent information, the extensive amount of logical information in the fuzzy ground state manifold just decrease continuously without any phase transition behavior. But if you think about parity conserving error, it indeed exhibits this kind of error threshold for original SOIK model as well as low rank variations of it. And it implies that there is some sort of phase transition. In the double Hilbert space picture, going back, and same for the Renyi 3, what it means is that after a certain threshold, there is some like hopping mean field condensate develops such that it acts like a parity breaking noise. And the situation is pretty similar to the case of the Ising model example I talked about. So this is related to the traversable wormhole in the following sense. So let's say you have like a two black hole and they are kind of maximally entangled by this line, and that facilitates the information traversing from one side of the black hole to the other. But you may find this setup is pretty similar to the setup I've considered. And you can ask, oh, what if one side of the black hole is like decohered? I mean, this black hole can interact with its environment and so on. And you can ask, oh, how does traversability degrade with the coherence? And so my answer is that if that like decoherence preserves like say something like a fermion parity, then basically you have a certain threshold. Your traversability will be robust up to a certain threshold. But if it's not, then it will just degrade continuously. All right, now it's the like final case, which is the U1 symmetry. Any questions so far? Okay, this was maybe too technical. So next, I'm going to talk about the physics of charge transport under a random unitary circuit. So there's been a nice exploring work about how the density matrix evolves under random unitary circuit, which conserves the, say, a U1 symmetry. And what they basically showed is that if there's a symmetry, there's a charge conservation, it implies that the charge dynamic is slow, basically diffusive. And I'm trying to reinterpret this result from the point of view of spontaneous symmetry breaking in this open quantum system. So for that, I'm considering a random circuit captured by a Brownian, so-called Brownian random circuit. So here, at each time slice, your density matrix evolves under this like Hamiltonian, but this Hamiltonian is written in this way, which depends on a Brownian random variable dB, such that at every kind of point in every time slice, this Brownian random variable is randomly chosen. But this is the coefficient, and the term preserves the U1 symmetry charge, so that entire dynamics is a strongly U1 symmetric. And if you average this over like all random variable, basically what you get is a Lindbladian evolution. So if you take the expectation value of the evolution of the density matrix, it's written in this way. And now if you apply this Choi isomorphism, basically what you're seeing is an imaginary Schrödinger equation where your density the Choi state of the density matrix evolves in this way, e to the minus t HL, where HL is a sum of square form. So like if like the magnitude of the Brownian random variable is kind of like set to be uniform across the site, although each realizations of the random circuit does not have a translation symmetry, after averaging, it will have a like average translation symmetry. Put differently, it doesn't have a strong translation symmetry, but it has a weak translation symmetry. And because of that, I can diagonalize my operator in this weak translation symmetry basis. And then basically, when I look at this operator correlation between two different times, it can be decomposed into this form. And the key takeaway here is that it's basically diffusive behavior, which is given by this exponent, is determined by the energy of this momentum eigenstate under this effective Hamiltonian, EK. So if your dispersion is quadratic, gapless, then you're going to have a normal diffusion. If your diffusion is like, say, linear, then you're going to have like a super diffusion, ballistic transport. If you have a very smooth, like a quartic or smoother dispersion, then you're going to have a sub-diffusive behavior. So basically, the low energy dispersion of this effective Hamiltonian determines the diffusive behavior. And now, but you can first ask this question. Whenever you have a gapless kind of degrees of freedom, there must be a reason. Either there must be a spontaneous symmetry breaking of continuous symmetry, or a system must be critical, or have being Fermi liquid, or there must be some reason. So initially I thought this is a little interesting, and then realized that there is indeed a spontaneous symmetry breaking. So because the dynamics is a strongly symmetric, you have a double symmetry, U1 for the upper layer and the other U1 for the lower layer. And then under this Lindbladian dynamics, after long enough time, we all know that it's going to relax into a maximally mixed state. So maximally mixed state or choice state of an identity operator is a proper ground state of this Hamiltonian. And because our Lindbladian is strongly symmetric, it can be decomposed into the smaller symmetry sector. Namely, the projection operator into each total charge sector is also the ground state of this Hamiltonian with zero energy. And what that means is that since each kind of choice state of the projection operator has a different kind of off-diagonal U1 charge, you can always form this theta state which spontaneously breaks the U1 off-diagonal symmetry. And because of that, what basically means is that if you think about any generic Lindbladian dynamics that is strongly symmetric, it's very likely that the steady state will always exhibit spontaneous symmetry breaking of strong to weak SSB, which is somewhat intuitive because if you think about Lindbladian dynamics, in the end, it will approach some classical mixed state, and you should lose the quantum coherence about any symmetry existing. And because of this spontaneous breaking of the U1 symmetry, you're getting some gapless Goldstone mode. And what I showed earlier is exactly that. And this kind of a gapless Goldstone mode can be constructed using something called a single mode approximation. So starting from some ground state, you can modulate the ground state by some density with momentum K. And then that is going to have some variational energy. And what's happening is that usually the numerator has a K-square dependence, but denominator has some K dependence such that in the case of, say, superfluid helium with U1 symmetry breaking, you have a linear dispersion. And what it means, so if you look at the denominator, it's something called a structural factor. So if your ground state has some momentum modulated kind of structure or spatial kind of structure, it's going to have a non-trivial K dependence. And that's indeed what's happening for the superfluid helium. But if you think about our ground state in this kind of frustration-free Hamiltonian, the ground state was a choice state of just identity. There is no interesting structure whatsoever. So you may already imagine that structural factor in this setup is just constant, independent of the momentum. And that's indeed the case. So if I skip all the irrelevant parts, basically what I can show is that the energy is kind of K squared if you have a U1 conservation symmetry. And if you have a conservation more than the U1, like U1 multiple, it can have a smoother dispersion, meaning that your diffusion will be slower and slower. And now it kind of tells you something more interesting about diffusion in a specific symmetry sector in the following sense. So when your Hamiltonian has a lot more symmetry, it's possible that your dynamics is fragments of Hilbert space in that naively, if they all have the like a same symmetry charge, you may imagine that like all bases are kind of connected to each other in the end. That like even if you start from say a specific basis, you may get some weight on the other basis as well. But in the case where you have a say dipole conservation or like octuple conservation or things like that, it's possible that the Hilbert space can be fragmented, like they don't talk to each other, and basically the steady state will further decompose into the projection onto each Krylov subspace. And when that happens, basically I can consider there's a choice state of the Krylov sector projector as a new ground state and trying to calculate the excitation with respect to this, like I did for the other single mode approximation. And because this Krylov subspace is fragmented for some interesting reason, like it has a very weird spatial modulation, spatial pattern of the charge such that it kind of prohibits it being connected to the other sector, its structural factor will be actually non-trivial. But then what it means is that now you have some k to the certain power for the numerator, but k to the another power in the denominator, meaning that your dispersion will be kind of flatter and make the diffusion faster. Indeed, we did a simulation and basically show that although in a dipole conserving system, you expect the diffusion exponent to be 4, z equals 4, we found specific Krylov sector where it exhibits the diffusive behavior rather than the subdiffusive behavior. So this is basically saying that Krylov space resolved hydrodynamics can be very different from the average dynamics. So yeah, basically I can skip this. So the summary is that this spontaneous symmetry breaking in this kind of open quantum system provides some unifying framework to understand various different kind of information dynamics. And I talked about Ising Z2 symmetry, but it can be always generalized to any like G or ON symmetry. I talked about also fermion-Perry symmetry. And finally, the charge Yeon symmetry. So there's a landscape of like a different mixed state. So although like today I only talked about the strong to weak spontaneous symmetry breaking, you can also think about symmetry protected topological, various different topological phases like SPT under decoherence or topological order under decoherence. And also you may want to understand kind of fault tolerance of the error correction scheme. So when I talked about this error correcting the Toric earlier, that threshold assumes that your measurement is perfect. What if your measurement is imperfect? And then you have to think about like measuring like over and over. You have to think about kind of space-time circuit a bit. And this, what I can show is that there's a space-time circuit a bit kind of maps to the some SPT defined in the higher dimension, and the robustness of the fault tolerance protocol maps to the robustness of this SPT and higher dimension under decoherence. So, and those kind of like topological phases can exhibit robustness beyond this strong to weak SSB framework because there is a higher form symmetry involved. So even if microscopically you don't have a strong symmetry, there can be emergent strong symmetry that basically provides some robustness of these topological phases. So yeah, let me conclude with thanking to my advisor. Thank you to my collaborators, Makinde and Yeon for the last part of the talk, Yeon Kim and Ehud Altman for the second part of the talk, and Chen K, Ijang, and Chao Ming for the first part of the talk. Yeah, thank you.
Okay, question?
Pardon? Oh, sorry. What I mean is that if you think, sorry, W, so this like if you think about some density matrix decompose into a like, yep. Oh, so what I'm saying is that if you think about the steady state of the Lindbladian dynamics, which say preserves the dipole conservation, so on, then that steady state can further decompose into this projection to the Krylov sector. Yeah, yeah. Or if you think about any kind of evolution of the, say, certain pure state under this Lindbladian dynamics, it's basically going to have a like block diagonal form where each block corresponds to a certain charge sector, right? You'll have a zero kind of off diagonal element between a different charge sector. But I'm saying it's a further, there will be further zeros because different Krylov sector will not talk to each other. Yeah. So there, it seems like there's some like emergent kind of conserved charge, although that conserved charge is kind of hard to express. So Krylov sector, you can kind of thought of as like there is some index valued symmetry charge. Right, right. Right, right. Yeah, yeah, I think so.
Okay, more question? Okay, if not, let's then John again.